Okay, thank you. Hard act to follow after those two presentations. Very interesting. And it's this time of the day where you're starting to get a bit of a sinking feeling and need some coffee, so I'll try and keep it light. For those that don't know me, my name's Matthew Thurbon. You can call me Turbo as well. I'm an SE team lead at Arista. I've been for almost 6 years. Today, I'm going to talk to you about AI networking, or networking for AI. I've been going to AusNOG for almost six or 7 years now. And fortunately or unfortunately, depending on your point of view, I'll be presenting instead of Rich Bayless, as he normally does. Okay, so just a quick note about my journey in the ICT industry, networking industry. I've actually been in the industry for 30 years. My first job, straight out of high school, fresh-faced, 18-year-old high school, was at Alcatel. Alcatel, as you know, had a manufacturing site back in '94 out at Moorebank. And so I was an electronics trainee, and one of my first jobs was to go dumpster diving for these Touchphone 200s, which you're probably all familiar with and had on your wall, right? The reason for that, though, these were due to be used as refurb telephones, so I had to rip open these cases, rip open the PBAs and PVCs, have a look if they were not eaten by cockroaches, and feed them back into the manufacturing to get tested and reshelled in brand new touch phones. So that was my journey. Shout out to all my Nokia friends still here. So yeah, this leads me 30 years down the track. I've worked for a number of different networking vendors in various sort of life cycle along the years. One of the things I'm sort of most proud of is still having my hair, one, and meeting a lot of great, bright minds in the industry, a lot of engineers, and making a lot of friends as well. So yeah, today we're going to talk about AI networking. So first things first, we're going to have a look at what the hyperscalers have been doing. So, you know, every single day you get new news of some hyperscaler, so Meta, Oracle or Google Cloud building exaflops worth of AI clusters, right? So yeah, we're going to look inside what they're doing, and then what I'm going to try and do is break it down into sort of basic networking fundamentals, seeing what's happening behind the scenes, but focusing really on the networking aspects, not necessarily on the compute or GPU aspects, but mostly about the AI interconnects. So looking at Meta, Meta have built a Gen AI Llama 3 infrastructure. This was announced back in March of this year. One important thing to note, they built a 24K GPU Ethernet cluster. And they've actually built both a RoCE, or RDMA over Converged Ethernet, and an InfiniBand cluster for large Gen AI workloads. So Llama 3 is running on the RoCE cluster without any bottlenecks. The other thing they're doing is they're building it with Arista's 7800 series, so a Jericho 2 platform as the AI spine, and they're leveraging their Wedge 400 and Minipack Open Compute project rack switches as well. On the other cluster, they have a NVIDIA Quantum InfiniBand fabric, and both clusters are built using the Grand Teton in-house open GPU design hardware from as part of the Open Compute project, right? So cloud providers are building these AI clusters. God knows how much power they're using, but I'm going to sort of break it down into like what would it take to build one of these clusters and the network requirements as well. So in terms of AI applications, you know, the jury's out about a number of AI applications, their value to us as human society. There are a number of interesting ones, being IBM Project Photoresist. They've identified a new molecule. Typically takes about 10 years to identify a new molecule, and it costs 10 to 100 million. And this was be able to reduce down to months. In addition, they've developed a new photoacid generator, which is used in lithography, which is a key process in making computer chips. So this sort of smells a bit like Skynet to me. So computers, AI building other computers. But you know, there's a lot of great applications, but I'm not here to judge these. What I want to talk about is the networking aspects and what's happened to things like performance of GPU over the years. So if we look at the improved performance per GPU, so the big player is NVIDIA. So if you look at NVIDIA over the years, from Pascal through to Blackwell, so 2016 to 2024, 8 years, the GPU performance has increased by 1,053 times. The lower floating point results in lower precision and lower range, but also lower bandwidth and memory requirements, which is great for AI networking. In terms of an AI application here, Blackwell creates the first ever FP4 generative AI bunny, a 4-bit bunny, they're calling it. I'm not sure if it's coming through on the screen, but there's a clear, when you do it in a big screen, there's a clear difference between the two. So as a prompt, the prompt was a close-up photo of a rabbit forest in spring, haze, bloom, dramatic atmosphere, centered, rule of thirds, 200 mil, 1.4F, macro shot, right? So these are the things we're testing it on. There's a whole lot of other applications, but in terms of, again, looking at NVIDIA over the years, so from Pascal through to Blackwell, the energy consumption for token generation has dropped by 45,000 times, right, over the last 8 years. This is based on large language models where token is a basic unit of meaning, such as a word or a punctuation mark or a number. So we've got these servers. What do these servers look like? Here's an NVIDIA example. Again, NVIDIA are the biggest player in the market. The NVIDIA have a DGX, so which is an NVIDIA-built system. And there's also HGX, which is an OEM system from companies like Supermicro, Dell, and HPE. And so what you'll often see is a collective of GPUs. So typically you'll see 4 to 8 GPUs in a system or a server. And connectivity-wise inside that host, so from internal CPU to GPU and GPU to GPU, it's a mix of PCIe and NVLink. So very, very fast, very low latency inside the server itself. In terms of AMD, AMD have, again, built 8 GPU clusters, so Supermicro, Dell, and HPE OEM. And again, inside, so as I said, NVIDIA has Nickel for the inter-GPU communication using NVLink. And this one here, AMD using a thing called Infinity for, as a mix of PCIe and Infinity. So there's different sort of standards inside a host, a cluster of GPUs. And the Intel example, again, looks like that. It's a mix of GPU to GPU, is a mix of PCI and alternate pathways. So what happens when you have some compute that needs to go beyond this 8 GPU cluster? Now, I'll take a step back and just quickly talk about power requirements for these GPUs. Again, got a graph here. On average, we're looking at about 750 watts per GPU, let's say plus a 500-watt server. Again, I've done these calculations on the back of a beer coaster, so don't quote me on this. A normal DC rack is about 6 to 10 kilowatts. GPU racks are generally around 16 to 20 kilowatts. The average DC capacity, given small and large Ds, is about 10 megawatts. DCs is about 10 megawatts. I think the bigger ones, like the next DCs of the world, are 50 to 80 megawatts. So 15K GPUs amounts to 18 megawatts, and 100,000 GPUs amounts to 150 megawatts. So it's a lot of power. One day we'll probably get to 1.21 gigawatts, but we'll see what happens. Okay. So as I said before, talking about the networks involved in GPU to GPU communication inside the host. So NVIDIA has a proprietary thing called NVLink, which is used inside the server. AMD has Infinity, and I don't think Intel have a name for theirs, but essentially it's a way to connect the GPUs within a server host. Now, recent announcement, sort of in May timeframe, May, June. There was an announcement, a consortium formed, where everyone except for NVIDIA has formed an Ultra Accelerator UA-Link consortium, right? So what does that tell you? It means that NVIDIA is the big player in this market. They got a stronghold. They do great things, but NVLink's a proprietary mechanism, and what the rest of the industry is doing is trying to come up with the equivalent NVLink for an open standard as such. So we're calling that the UA, Ultra Accelerator Link, so a GPU accelerator. Now, talking about GPUs, you'll often find us different flavors of GPUs. So typically we always talk about GPUs, so they're optimized for parallel processing, making them ideal for training large AI models on top of its original use of graphics processing. So typically when we're talking about GPUs, it's NVIDIA, but some other chip makers use the term GPU. TPU stands for TensorFlow-based AI workloads. So these are developed by Google for neural networks, offering extreme efficiency for specific tasks. And DPU, so there's a couple of more acronyms for DPU. There's Deep Learning Processing Unit or Data Processing Unit, but essentially it's optimized for data processing, and it's often embedded in things like SmartNICs, so NVIDIA Bluefield and AMD Pensando. So we've got these XPUs, let's call them. So inside a server, they're connected usually by a PC bus, right? Or using that internal NVLink or equivalent upcoming UA link. And that typically supports 4 to 8 GPUs across the PCO bus. And then what we have is the XPU to XPU interconnect. So NVIDIA has NVLink, and that can transfer internally at 1.8 terabytes per second between GPUs. On top of that, there's actually an NVLink rack-level switch capable of supporting up to 576 fully connected GPUs in a non-blocking compute fabric, right? So a single computational domain. And again, as I mentioned before, there's currently a work in progress with a consortium of everyone but NVIDIA to develop the Ultra Accelerator Link, establishing an open industry standard for standardizing AI interconnects in the future. Now, the third one is what I'm really going to talk about in terms of networking and AI fabrics is the server-to-server interconnect. So this is either an Ethernet or an InfiniBand by NVIDIA network to connect servers that contain XPUs, right? So the connection is often termed scale-out, so it's typically what you see as a leaf-spine scale-out model, where multi-GPU domains are connected via Ethernet IP or InfiniBand fabric to form large computational networks, right? On top of that, recently there was another consortium called the Ultra Ethernet Consortium was formed to deliver everyone else's InfiniBand. Just a note on these frameworks that are available for managing GPUs. Different vendors will have their different libraries available to manage these computational domains across GPUs. So we've got Nickel, I'm going to call it Nickel. We've got Rickel from AMD. We also have PyTorch, TensorFlow by Google, Keras, which are all open source, as well as some from Microsoft and AWS. Now, back to being a network engineer. We've got these new servers. These servers are typically having 200 gig or 400 gig NICs. And where do I plug them in, right? So the average enterprise is focused on typically just compute, right? So standard DC would be a layer 3 leaf spine, scale out, so you could scale this to 2, 3, 4 spines, scale out the compute leaves. Typically the compute these days, particularly in the Australian market, is sort of 10 gig uplinks, dual 10 gig uplinks, or even 25, going up to even 100 gig for things like hyper-converged infrastructure or storage. So yeah, where do we plug them in? So what does an AI networking infrastructure look like? So again, the front-end network is what I talked to you about before. That's your typical DC network. We have a back-end network, which is behind the compute, so behind the GPU server farm. We also would have a storage network, as well as in-band and out-of-band network, right? Digging a bit deeper, what do these clusters look like? So, as I said, we've got front end, typically 100 gig leaves, 25 gig leaves, 10 gig leaves, AI storage. But what's sort of new is these hosts. So all these GPU servers have 8 GPUs, and these GPUs can be connected to a back-end network, which is what we're calling an AI scale-out fabric. So as I said, these servers are connected via 200 gig, 400 gig NICs, and in the future, 800 gig and 1.6 terabits per second. So yeah, that's a picture of the network. How do we connect GPUs once we've got them across AI fabric? So in terms of what NVIDIA do, they have what's called a rail. So if you look at a standard setup, you've got CPUs, In the standard setup, you've got CPUs connected to a single switch. In the rail optimized network, you have a rail is comprised of GPUs that have the same rank within hosts and clusters, and they're connected to the same network switch. Now, what happens here? What that means is that if you want to communicate from GPU 0 to GPU 3 in host 2 and the other host, instead of going straight out to the fabric, which is higher latency, it will leverage the NV link internal to the server to reach the GPU across in the other server. So that's the rail optimized approach. So AI workloads, in terms of like the data that's been pushed back and forth, what does the AI workloads look like? So AI workloads are extremely computationally intensive and exceed the memory available on a single GPU. Therefore, the workload must be split across a cluster. So that cluster can be within a host or across a whole AI fabric. So these GPUs perform algorithms, calculations, and share the results amongst each other. So these are commonly called what we call a collective operation. So they include broadcast, ring reduce, all reduce. There's a whole lot of different collective operational models that can be used for the GPUs to communicate. But most importantly, all GPUs have to wait until all GPUs have shared their messages and passed the results. So this workload is stalled until this happens, and this is commonly known as what's called a barrier. And as mentioned, the GPUs within a host have their own internal fabric, which is typically lower latency, and then you have, if that goes outside a fabric, which is slightly higher latency. Hold on. So what's different about the workloads? It typically uses RDMA, kernel bypass, for better performance. There has to be tight time synchronization between traffic flows. The flows themselves, there's a very small number of large-sized flows, sort of around 2 to 3 flows per NIC. Very little entropy and short periodic bursts of network activity followed by compute. So what this means, it's highly susceptible to collisions. And what the key metric is in terms of AI workloads is job completion time, right? So the job completion time is essentially the time between launching a job, processing the data across a cluster of GPUs or accelerators or across an AI fabric or an Ethernet fabric, and posting the results. Another important metric is time spent in networking. So we want to reduce that time in networking down to the absolute minimum. And again, as I mentioned before, the slowest member determines the overall performance. So what is the requirement for AI networks? We want to scale out capacity. We want a fast, lossless network with zero oversubscription, and is often over-provisioned, which I'll talk about later. As I mentioned before, we've got graceful handling of large synchronized flows, and we have fast transfer from RDMA over converged Ethernet, so RoCE and RoCEv2. What we want in an AI network is visibility and telemetry. So we want to be able to identify bottlenecks in the network or the application. How do we do this? We generally do this via real-time streaming telemetry. It needs to be reliable and resilient and open and interoperable, right? That's the keywords. Open standards always wins in the end. So RDMA, just a refresher on RDMA. So it's the remote direct memory access, which is remote memory management capacity that allows servers to move data directly between application memory without any CPU. So it's essentially a CPU bypass. In terms of RoCE, RoCEv2, my favorite film in the series. Not my favorite film. That would be Star Wars. So RoCEv2 is a network protocol that allows RDMA over Ethernet. RoCEv2 extends that essentially to adding a UDP or an IDP header, so essentially layer 3. So RoCE is used, it's nothing new, it's used a lot in storage networks, but RoCEv2 has been leveraged in large-scale AI networks, and it provides the following advantages, which is basically allowing routed Ethernet networks, again, over a layer 3 leaf-spine fabric or EVP and VXLAN fabric, so large scale-out ECMP fabrics, as well as the ability to do IP QoS using DSCP and other things you can tune, such as IP congestion control with ECN. And again, using a UDP header provides more entropy for better ECMP load balancing. Now, this is not NVIDIA bashing, it's just to point out pros and cons. NVIDIA's proprietary, Ethernet's industry standard. To my knowledge, NVIDIA current products are around 400 gig. I'm not sure of the roadmap to 800 gig, but please call me out on if there are 800 gig. Ethernet has a very strong roadmap, and I'll talk about that soon, with 800 gig and beyond. InfiniBand has a centralized control plane versus a distributed control plane with Ethernet. NVIDIA uses a subnet manager to control the entire network, whereas in the Ethernet case or a layer 3 IP fabric, the routing protocols make local decisions. And again, NVIDIA uses single hop, whereas we can use RoCEv2 on layer 3 scale-out multi-hop networks. So what's been happening in the industry is, as I mentioned before, the Ultra Ethernet Consortium was formed in 2023. It aims to develop a standard for interconnection for AI and HPC data centers. There are currently 55 members. I believe they're very close to publishing the 1.0 spec. So what that gives on top of what, say, something like RoCE already provides is multipathing and packet spraying, flexible ordering, more optimized congestion control for AI workloads, some improvements to end-to-end telemetry and also security. So this is, it does say Ultra Ethernet Consortium, but it's essentially the whole UEC stack, all the way from applications down to the Ethernet physical layer. So again, Ethernet has advantages over InfiniBand for Gen AI networking fabrics. All network engineers know about Ethernet. It's in all other ecosystems, so that makes it easy to have sort of things like end-to-end visibility. And InfiniBand is essentially standing alone on its own, right? Again, Ethernet has a roadmap for 800 gig and beyond with a clear path to 1.6 terabits. Okay, so what's different about AI connectivity? Again, I mentioned before, we've got 200 gig and 400 gig to the NIC, from the NIC. In terms of SerDes speeds, we've got 50 gig PAM4, 100 gig PAM4. Copper DACs generally aren't used as much these days in this sort of environment. We've got active electrical cables, AOCs, active optical cables, and optics. And sometimes you might have to convert between PAM4, 50 gig PAM4 and 100 gig PAM4. So for connectivity between switch vendors, again, this is an open ecosystem. You can have multiple different switch vendors. You've got to think about electrical lane speed, physical form factor. The introduction of 400 gig and 800 gig as well has introduced a number of different form factors, which many have talked about, and I'm sure the flex optics guys will too. So QSFP DD as well as OSFP using 8 by 50 lanes, OSFP writing heatsink with 4 by 100 electrical lanes, QSFP DD using 4 by 100 and QSFP 112. So again, it's a bit of a minefield as a network engineer selecting the right form factor and so on. So again, talking about thermal performance, so if you're thinking about large scale-out fabrics, we want the industry and customers to always have the lowest possible thermal performance, which relates to power utilization. So comparing OSFP to QSFP DD, QSFP DD is just an extension of the existing 40 gig and 100 gig QSFP DD. OSFP has an integrated heatsink, 50% more surface area, and better airflow along the entire module surface for the OSFP. So they generally operate 10 to 15 degrees C cooler than QSFP DDs for the same platform. An important one is the mean time between failure, which is an increase of 10 degrees C increases optics failure by 2 times as well. So OSFP has a clearer roadmap to 800 gig, 1.6 terabits using OSFP XD. And there are further efficiencies with the upcoming linear drive pluggable optics, LPO. Moving on to LPO, in its simplest form, you look at a traditional pluggable optic. The optic itself has a DSP and photonics on the other side, and that's connected to the switch chip on the switch itself. What does LPO mean? Essentially, it just means the DSP is no longer on the transceiver itself. You ask, how is that possible? So Merchant silicon such as Broadcom Tomahawk 5 and Jericho3 has an advanced DSP technology inside the switch chip itself. So that brings down the overall power consumption as well. So there's the LPO MSA with all these vendors who are contributing to that standard as well. So comparing traditional DSP optics to the LPO, it's around 15 watts for 800 gig DSP traditional modules as opposed to 7 watts. So it's under half the power. In terms of delay, so this is very important. AI networks is the latency is around 100 nanoseconds through the DSP, and it's down to around 1 nanosecond delay through the actual module. Cost is much less, 60% of the cost compared to the DSP. Obviously, DSP is mature. It's in high volume. The LPO is expected to be volume in sort of late 24, early 25. In terms of the ecosystem, DSP currently has a lot of multi-vendor interop, plug and play, standards-based, and the LPO MSA has just been announced. So one of the things that needs doing in terms of LPO that requires tighter integration with the system, which means you have to tune the actual switch chip itself. And currently, to my knowledge, at least in terms of the merchant silicon world, it's currently restricted to Tomahawk 5 and Jericho 3 platforms. Okay, last 3 slides. I'm just going to give you an example of what a small AI network design looks like. Small is subjective, but essentially the scale is 64 by 400, connecting 64 by 400 GPUs, or 128 by 200 gig XPUs. In this particular case, we can use a Broadcom Tomahawk 4, 64 by 400 gig. I know that in the Arista world, we have both QSFP DD or OSFP switch options, and that provides 25.6 terabits per second. In this particular case, we're just connecting one switch, so that means there are no flow collisions because we have that single ASIC. Another thing is you have to tune in terms of AI networking. We have to be able to handle incast at the receiver, so we use things like ECN and PFC. In terms of Broadcom Tomahawk 4, it's a fairly shallow buffer, a low latency switch. So there does require for AI workloads to be moderate tuning required on the actual platform itself. Again, moving up to moderate, again, that's subjective, but what I'm talking about moderate is 576, 400 gig XPU NICs. In this particular case, this is what we call a scale-up model, so we can use a chassis. In this particular case, the chassis supports lots of line cards to support up to 576, 400 gig, either QSFP DD or OSFP. 230 terabits per second. We're combining the AI leaf and spine in a single chassis, so it's scale up. Again, no flow collisions between line cards and fabric. It's over provisioned, last slide. And high availability. So high availability is provided by the redundant fabric, supervisor, the fan, and the PSU. Again, handling incast, we're using ECN or PFC, and because it's a deep buffer system, the Jericho2 or 2C+, it requires minimal tuning. Now, when we get to what we're calling large, this is up there with what the cloud scale providers are sort of shipping. So this particular scale is 18,432 by 400 gig XPUs. At the spine, we have a Broadcom Jericho 2C. Again, as per the previous example, it's 576 ports. And again, we have connectivity from the servers or the GPU servers to the AI leaf. Again, in the first example, it was using Tomahawk 4, the low latency switch, which is 64 by 400. Some additional tuning is required because you've got this AI fabric. So the AI fabric means you have to do things like dynamic load balancing, source load balancing. And one of the last important things is that quite often the fabric will be actually over-provisioned. So 1 to 1.2 over-provisioning on the leaf. You might ask why that is the case. Essentially, if you fired up this, let's say 10K or above cluster, with each of the optics having 5 years of mean time between failure, your first optic failure will occur in the first 4 hours, right? So it'll be a constant case of, you don't want to go below 1-to-1, so optics fail, heat, thermal performance is very important in reducing those failures in an AI fabric. And I believe that is my last slide.